This question is an oscillation question, but also it throws back to your AS. Let's read the question. A small wooden block or a cuboid of mass m floats in water as shown in figure 3.1. So if you remember certain questions from your AS, it's very similar, right? You have something that is floating and you are asked to state the names of two forces acting on the block when it is stationary. So stationary here kind of implies that the block is in equilibrium. Very nice. So what are the forces? There's definitely weight because, we're all under gravity, the influence of gravity. And there is also some form of upthrust. Okay, so you could say upthrust or buoyancy, but those are your two forces. Okay, are you ready for some action? Part B. The block is now displaced downwards. So we're going to put our hand on the block and push it down, like the world is pushing down on you because paper 4 coming soon. Okay, anyway, so we're going to push it down a bit so that the surface of the water is higher. So when this surface of the water is higher, hopefully you remember that this means that there is more water displaced. And because of this, the upthrust is bigger. Upthrust increases. So state and explain the direction of the resultant force. So previously in the first drawing, okay, your upthrust force, let's say FU for FUP for upthrust is equal to mg because it's in equilibrium. So when upthrust increases, it means that the upward force is greater. So right now what we have is a greater upthrust and then a smaller, the same weight. So I will say the direction of the resultant force is upwards. But stating is not good enough. I also need to explain. You can say that the upthrust has increased and is now greater than weight. Okay, upthrust has increased and it's now greater than the weight of the block. Okay, but why did we displace the block or push the block down a bit? Because we are going to let the block oscillate. So once we push down and let go, because the upward force is bigger than the downward force and the resultant force, the net force, is in this direction, this block will begin to bob up and down and up and down. That is where we get oscillation. Part C. The block in B is now released so that it oscillates vertically. The resultant force acting on the block is given by this equation, where G is the gravitational field strength, X is the vertical displacement of the block from equilibrium position, and previously the questions have also mentioned that A is a cross-sectional area. Cross-sectional area of the block, and then rho is the density of water. All right, so explain why the oscillation of the block is simple harmonic, are simple harmonic. So first things first, if you want to explain something is simple harmonic, recall that the definition here says that acceleration must be proportional to negative displacement. So there are two things that you must talk about. The first one, you have to mention the proportionality relationship. And the second one you have to mention is the direction. The fact that A, acceleration, and displacement is opposite. Okay, so please make sure you mention these two. All right, but first things first, I need to get rid of or rather invite A into the equation. So I'm just going to write here very quickly as a draft. This is A, G rho X. Okay, so I could say A, rho, and G are all constant. Hence, force F, or the resultant force, is proportional to the displacement. Okay, so this is the first statement, F is proportional to X. But teacher, how do we invite acceleration? Well, you can just add a quick line here and say, since F is MA, so for the same block, F is proportional to A, hence A is proportional to X. Okay? So F is proportional to X, but F is also proportional to A, so A is proportional to X. All right, last part, we need to talk about the direction, which is shown by the negative sign. So the negative sign shows that F and X, or you can say A and X, are in opposite direction. Okay, so the 2 marks here, 1 mark is when you mention A, rho, and G are constant, and then F is proportional to displacement. 1 mark, B1. The second mark here is negative sign showing that F and X is opposite direction. So in this case, this mark scheme didn't emphasize that you should or you need to show the fact that force is proportional to acceleration and then acceleration is proportional to X. So it's a given, and then if you write this, it's okay. It actually shows a better understanding of how these things are linked. All right, that's part 1. Okay, part 2. Show that the angular frequency omega of the oscillation is given by this equation. So we have the equation F is equal to negative A G rho X, A, G, rho, and X. Okay, and now we are going to substitute. Okay, so before we substitute, I need to find a way to compare this with because the way to get omega, I need to compare this with the general equation of simple harmonic motion. So you can treat this chapter like very mathematics. Just like, for example, there's a general equation of a straight line and a general equation for curves and parabola. So there can also be a general equation for simple harmonic motion. And this general equation is A is equal to negative omega square X. So with this A is equal to negative omega square X, I need to write this as MA, and this is negative AG rho X. So now A will be equal to negative bracket AG rho divided by M X. So you see what I did here? I isolated it. So now I'm going to compare with A is equal to negative omega square X. So we have A as the subject of your equation, which was the whole purpose of this exercise. We have X on the other side, and everything in this bracket, ladies and gentlemen, boys and girls, is your omega square. So you can then say, hence, omega square is equal to A G rho over M. So omega will be equal to square root of AG rho over M. Okay, so this part of the proving is pretty straightforward. As long as you arrive at this equation or this step, you get 1 mark. Okay, and then you equate this one to omega square, you get another mark. Actually, this is M1. So you must show this to get A1 mark. So whenever you look at the mark scheme and you see M1, it means that it is possible to get M1A1 full mark. It is possible to get M1A0, meaning your method is correct, but your answer is wrong. Maybe there's a algebra mistake or you didn't square root. Okay, you could also get M0A0. So M0A0 meaning your method is wrong and obviously your answer is wrong. M0A1 is not possible, not allowed. Which means if you use any other methods besides using the general equation of simple harmonic motion, you will not be given any marks, even if your answer is correct. All right? So very important to know the common steps to solve questions like this. All right, that's it for part 2. Let's move on to the next part. Part D. The block is now placed in a liquid with greater density Sure. Okay, so it doesn't really matter that the density has changed. That only affects the value of omega, right? As long as inside the liquid itself the density is the same, our object is still in simple harmonic motion. It will change the frequency or the value of omega or the period, but otherwise everything else should stay the same. The block is displaced and released so that it oscillates vertically. The variation with displacement x of the acceleration for the first half oscillation is shown. So when you look at this graph, it is a graph of acceleration against displacement. It is familiar, but a bit different. And then you might be thinking, Miss, where is it a bit different? What means a bit different? Well, you look here. This one, the line kind of stops at this point here, you know. So I'm just going to carve out this point. And this one, I don't know about you, 2, 4, 6, but this point here looks like 0.016 meter. Okay, and if I check out the other side, it seems like the maximum value of displacement is 0.02. Very interesting. Okay, so you are asked to explain why the maximum negative displacement of the block is not equal to the maximum positive displacement. So they are like trying to be a bit sneaky. Instead of using the term amplitude, because you know what, you guys, maximum displacement is amplitude, what, right? So instead of using the word amplitude, which is what maximum displacement is, okay, they decided to just use maximum displacement and everyone loses their brain cells. Please don't. Okay, so this is amplitude. So basically they're asking you, why is the amplitude not equal? And the only reasons why the amplitude is not equal is because there is energy loss. Here's another hint. Let's say you totally cannot think of why, and then you're very confused because remember we just did part A where you draw the forces and you're like, did the forces change? Is the upthrust different? And then your brain goes down into a rabbit hole. Come back. Before you are tempted to go to a rabbit hole, and this is only question 3. This paper very long. You don't go rabbit hole everywhere. You will check out this part here. Determine the decrease in energy. So this is also another hint. If there is a decrease in the energy of oscillation, this one means what? It means there is damping, you guys. Okay? So if there is damping, this is why the this is why the amplitude drops. So damping here means loss in energy. And the energy of oscillation is equal to half m a square omega square. Okay? So the amplitude decreased because the energy decreased due to damping. So I would say something along the lines where the amplitude, aka maximum displacement, decreases due to damping. The oscillation loses energy. If you want to level up a bit more, you should also mention what causes energy to be lost. Okay, loses energy due to either friction or viscous drag. Remember this AS1, that's this viscous drag. Viscous drag. All right. So the mark here is actually when you say that there is damping due to viscous drag. This one is P1. Right. But the whole idea is the energy decreases, and throughout the question, they try to hint at you that the energy is decreasing. Okay, that there is damping. Speaking of which, now we have to find the decrease in energy. Let us revisit the equation a bit. Some of you may be thinking, Joe, very hard to remember this energy of oscillation. Well, here's a shortcut only. But you know, energy of oscillation is half mv squared. And this one is the fastest, you know, actually it's half m, it's ke plus pe lah. But this will be half m V max square, maximum KE, if the potential energy is 0, meaning when the object is moving the fastest. So this one will be half m. What is V max? A omega square. That's how I remember that energy of oscillation is half m a square omega square. All right. Or you could just memorize it. All right. But this is how I memorize it. I mentally go through the 4 steps in my brain because I can't trust my memory, you know, but I can trust my algebra. All right. So let's say you already came out with the equation, right? And now you want to find the change in energy. So this will be half m. So the only one that changed is the amplitude. So half m a1 square omega square minus half m a2 square omega square. I can factorize all the constants and leave a1 minus a2 square. Okay, so now I can substitute. I have 0.57, but wait a minute, what is our omega? How do we find omega? Because the question didn't give us anything but this graph. So remember how I say you must know the general equation for simple harmonic motion, which also happens to be the equation for this graph. This is A against X, which is why if you want to find omega, you can substitute a value inside, or you could look for gradient, which I will do so now. Okay, so your omega square, because you know you compare with the equation, let me use a different color. You compare with the equation y is equal to mx. So hence, gradient is equal to negative omega square. So I'm going to look for the gradient, and since I already have a few coordinates, I'm just going to use it. So the coordinate here is negative 0.02, comma. This one looks like 2.3. Yeah, 2.3. And because this point, right, you see, it's so neither here nor there, and it's actually quite hard to read the graph accurately, I have a certain point, which is this one. 0, 0. Okay? Proportional, ma? It must pass through the origin. Okay, la, can already. Don't worry your headache, don't worry your brain. If not, right, you whenever you use a value that is, because the line is quite thick, and whenever you use any other value, what will happen is that your values will run very far, because this is 0.001 for one box. That's a lot when you take and divide. Okay, so I'm going to put that into my values. Okay, of course, as long as you read with reasonable accuracy, you should not be penalized, but it is safer to use points that you know for sure passes through the corner, such as this one and this one. Okay lah. All right, so let's not worry too much about that. Let me arrange back the screen size and let us calculate now. So this would be 2.3 minus 0 divided by negative 0.02 minus 0, and this is your gradient, which is negative omega square. So my omega square is 2.3 divided by 0.02. Let me press my calculator first. This is 115. Okay, so this is how you find your omega square. Use the gradient. You may be asking, Miss, can I substitute values? You can, but it's generally not recommended. Okay, so finding the gradient is easier. Substituting the value most of the times is allowed, but not recommended. Okay, so I'm going to move on to go back to the question. So this was where we last stopped. We have to sidetrack and find omega, which is why, you know, sometimes the question is hard, not because it's hard, but there's like a hidden step. This is the hidden step. You have to find omega square. How do you know you need to find omega square? Well, you write out the equation and you notice the information is missing. Then you go and find it from the previous parts. Okay. So from here, my omega square is 115. Very careful, no square root. Or you square root, then square again, if it makes you happy. Okay. So the initial amplitude is 0.02 square. And then in the positive direction is 0.016 square. Okay, so we'll look back at your graph again. This is 0.016. This is the maximum displacement here. And the maximum displacement in the negative direction is 0.02. So 0.02, 0.016. So we will plug this into your equation and press your calculator. And it will give me an answer of 4.72, 7196 times 10 to the power of negative 3 joule. Okay, so if your answer is slightly different, it's okay. Just show you're working very clearly how you find the gradient. Okay, and what value is your gradient? So I can see that, oh, whatever value of gradient you have, you substitute inside here, but it should be reasonably close to 115. Okay, so that's all. So where do you get your marks? Well, the first one is writing this equation. Either you write energy of oscillation is this, or one of this equation is good enough. This one is C1. Okay, you looking for omega, or omega is equal to gradient, is C1. So they are not actually too fast about the calculation, as long as you show reasonable evidence. But of course, if you didn't write this identity, and then it's quite obvious from your working that you look for the gradient and your value is the gradient, then okay lah, it's no problem. So as long as you show evidence that you use this identity to find omega square, you get 1 mark, and that you are using this equation together with amplitude, not x but amplitude, to find the changes in energy, which is the first amplitude minus the second amplitude, then you're okay. And finally, the substitution leading to the final answer is A1. Okay, recall the equation, find omega square, and substitute everything in to bring you to the final answer. That is your 3 marks. All right, that's it for the question, but I want to tell you something. So one way of thinking about this question or damping is that, they say the first half of the oscillation. So if I'm going to graph a more familiar graph for damping, which is x against t, okay, I'm going to zoom in here a bit so that I can draw. But you were given a graph of acceleration against displacement, right? And then the graph was something like this. Here is 0.016 meter, and here is negative 0.020 meter. So when they say first half cycle, okay, and it's negative because you push down the block, so we're going to start with somewhere here, negative 0.020. Let's say this one is meter. Okay, so we're going to oscillate upwards, and then that's all. That is the only oscillation part that we're looking at. So this part here is positive 0.016. Okay, and after that, of course, the amplitude will decrease, and attenuate. But our focus is just the first half of the cycle. Okay, so if you read the question carefully, first half. So if you think about damping on the AX graph, right, this is the only graph you're going to get, because after that it will just be, the graph will be like this, and then after that it will become shorter, and then shorter, and then shorter, and then shorter, but it's all the same straight line, so you can't really tell the difference. Okay, so the only way to observe the decrease in amplitude after the first half cycle, it can't be on the AX graph, it has to be on a displacement against time graph. So you can see the exponential drop. So when you draw the acceleration against displacement graph, you're going to go from here to here, and then the next cycle you're going to go from here to here, then next cycle you're going to go from here to here. You get my point, right? It's just going to be shorter and shorter and shorter, and then at the end there's no more. So the way to show the damping or to appreciate the decrease in energy is still always an XT graph. But damping can look like different format for different graph. And I'm just wondering, how would the velocity against displacement graph look like for damping? Because this one, the XT graph is what we're familiar with. But what about a VX graph? This is just a bit of an extension, just to grow your brains a bit, So we're going to start with negative 0.020. Again, this one is in meter. Okay, and then what we'll do is we'll start from here, and then this one will be positive 0.016. So it's going to go like this, and then it's sort of like spiral inwards with smaller and smaller Vmax. Your Vmax will decrease. It's kind of cool graph. Okay, so think of interesting ways to represent your damping, not just in the good old displacement against time graph, but also how does it look like for the acceleration against displacement and velocity against displacement graph. Right, that's it. That's a bit of an extension or growth for the question. It's not too bad, this one, as long as you hold on to your principles and apply them carefully. I'll see you in the next question. Bye.